Okay, I see a couple of you just joined. Again, I just want to make an announcement here that we will have unannounced quiz during the semester. Okay, not today. Okay, don't worry. So, but in the future, it's possible. But I will also have some announced quiz. Okay, for the that's for the announcement for the quiz. And also, please join the class on time, okay? On time. Most of the announcement will be in the beginning of the class, okay? So you might miss some important information. Although I recorded, everything will be posted online, but I doubt many of you will watch the video again. But so
I will say this, Dr. Zhang, if people are on campus, the internet is moving really slow today.
Oh, okay. That's the reason. So I see some of you come in and out. Is that because of the internet? Probably, yeah.
It took me 5 minutes to get onto this meeting this
Oh,
morning.
okay, okay.
I work on campus, so that's why I'm here.
Okay, okay. So yeah, just try to keep in mind and try to be on time, okay, on time, and I will have announcement in the beginning of the class. Sometimes those announcements are important, okay. What else? Let's see. Viscosity. That's what we have last time, right? Viscosity. Let me share my screen. Okay. I will actually. I think after today's class, I will post some first set of homework problems. Please start working on it. It's getting more and more serious when time goes on. Okay, and more difficult. And please practice. It's my recommendation, to you is really to understand this topic. You probably need to do some homework problem to practice, and in order to also earn a good score, right? To get the knowledge. Okay, let me share my screen. Let's continue on that. On the viscosity topic. Last time we were here, we talked about actually how to describe viscosity, right? Viscosity basically describes the stickiness of the fluid, right? Stickiness of the fluid, right? So the sticky the fluid is, the higher, the bigger the viscosity is. Okay, the viscosity become bigger and bigger, then the fluid is become more viscous, more sticky, more hard. Eventually, when the viscosity become very, very large, then the fluid become solid, look like more like a solid. Okay, if it's close to infinitely large, then the fluid is just like a solid. Okay, so viscosity is a property in the reasonable range, not reasonable range. It's a with a small value when it's in the fluid region. If then it goes to solid region, the viscosity become almost infinitely large. Okay, so that's why in solid mechanics we never introduce viscosity, because there's no need. Instead we use elasticity. Remember, elasticity also is a property that describes the deformation, right, for the solid. Okay, so that's viscosity. Okay, then viscosity, last time we stopped here, it changed with temperature. Okay, I don't know if you feel this. Some of the fluid, the viscosity change with temperature relatively more significant than the other fluids. For example, I feel myself, physically, I feel the engine oil, actually, the viscosity changes with temperature. Okay, when you I don't know if you use the same engine oil, sometimes in the winter, in Louisiana, probably doesn't matter that much. It's not that cold in the winter, but maybe in the north, the cold place, I think that when you go oil change, they change the type of oil in the winter, right? In the summer, it's totally, sometimes a different type of oil. And if you use the same oil in the winter, you feel it's more hard for the engine to run, and the gas mileage is bad in the winter. educated guess. Why is that? Do you feel that in the winter the gas mileage is a little bit worse than in the summer? You probably don't feel much in Florida or in Louisiana. You go to Kansas, maybe you feel, you know. Okay, actually, you know, let me tell you this. I live in Kansas for 7.5 years. You know, it's been a while over there. In the winter, you know, you don't even turn on the AC, right? In the car, the warm air, you don't need the air conditioning. It basically is the heat from the engine, basically, right? So in the winter, you basically don't need to turn on the air conditioning. But the gas mileage is still worse than in the summer when the air conditioning is on all the time. Okay, so you know the reason is because in the cold temperature, the viscosity of the engine oil actually is higher. Okay, it's the liquid is actually hotter. Okay, when the temperature is cold. Okay, so it kind of like this. Viscosity changes with temperature for liquid. Okay, does this textbook still have this plot? I think the early version had this viscosity versus temperature plot. Otherwise, I can refer you to a figure in the textbook. Surface tension. I think there is a figure somewhere. It doesn't matter. Okay, I just tell you what does it look like, right? So basically, look at this temperature. When temperature is low, the viscosity is high. When temperature increases, the viscosity decreases. Okay, right? Does that make sense? Actually, sometimes it's noticeable. Okay, it's reasonable. If it's hot, it's cold. It's almost freezing. You know, the fluid become hotter, become more sticky. Okay. But for the gas is a different story. It's just opposite. No, it's in a different range. Gas viscosity is much smaller than the liquid. It should not be put into the same figure. They're like a several order of magnitude smaller. So, but if you show the plot, then the gas actually. When the temperature increases, the viscosity actually increases. So that's how the viscosity change with temperature. Okay. Okay. Any questions so far? I think there's some correlation in the textbook, you know, to correlate the viscosity value with temperature. Okay, but I think you don't need that correlation. Usually, in the engineering table, in the appendix in the textbook, it shows the viscosity change with temperature. Okay, they usually give you the table with different temperatures and what the viscosity value, just like density, like other properties. Okay, viscosity change with temperature more significantly. Okay. Okay, I think we have a full class today. Hey, everybody's here. I have 19 of you, plus me, 20. That's good. Everybody came to class. Okay. So next item here I want to introduce about the viscosity is Newtonian fluid versus non-Newtonian fluid. Okay. Anybody heard about the word non-Newtonian fluid? You probably did, right? Yes? No? Never?
No, sir.
Oh, okay. So if you never heard about this is a type of the fluid that's very, very, very weird. Okay, Newtonian fluid is just basically like the regular fluid, water, air, whatever fluid. Okay, so basically the viscosity is uniform inside the fluid. although it changed with temperature, just I showed you in the previous page, but it changed altogether. Okay, as temperature increase, the viscosity decrease. Okay, but in the entire if you have a container of that fluid, the viscosity change altogether. So any location wise, any different location, the viscosity is the same inside the same fluid. Okay, so it's uniform. That's called Newtonian fluid. So basically it doesn't change, the viscosity value doesn't change from place to place in that fluid. Okay, but non-Newtonian fluid is the opposite. So it's possible for non-Newtonian fluid to change viscosity on different locations inside of one fluid, okay, with certain conditions. So the viscosity, for example, certain conditions, including maybe the pressure. If you push it, then it becomes harder. Okay, if you apply a force to it, it becomes harder. The viscosity change. See, the equation still, I want to bring back our equation again. That's the only equation so far you learned. Right, look at this. Is this the only equation we get so far? So any problem I assign you for a quiz, maybe you probably just go through that equation. That's the only equation. Okay, that's why I don't assign you a homework quiz today, right? So what this equation said is this: its viscosity is a property. It's not supposed to change. Okay, it's a property. So this is for Newtonian fluid. So whatever you apply a force to it, here, let's say shear force. Okay, then what happened to the fluid? This is action and the consequences, right? If you apply a force to the fluid, that will be consequences, right? Is that right? So what happened to the fluid? Is the viscosity going to change in that fluid? No, for the non-Newtonian fluid, no. So what changes is, this is constant for the Newtonian fluid, okay? What it will change is the consequences will be the deformation of the fluid. Okay. Does that make sense? Okay, that's the equation, right? Fully understand this? Guys, very important. Try to relate your reality to the equation, to the math. Okay, math serve a purpose. That tell you not only that equation, that actually tell you that story. When you apply a force to it, actually the fluid will deform, okay, with the shear force here, okay? Then the fluid deforms. Shear stress actually is per area, right? Okay. Then the fluid deform. Then the property won't change, okay? It's a property, okay? But for the non-Newtonian fluid, it's weird. So for the same equation, instead of still applying a force to it, okay? So instead of the deformation of the fluid, no, that fluid actually changed the property. Okay, so you apply a bigger shear stress to it. Instead of the deformation, the fluid moves. No, it's not moving, but the viscosity increases. Instead of the strain rate, du dy increase. Okay, so that's the difference between Newtonian fluid and the non-Newtonian fluid. Okay, which part of the right-hand side changes with the left-hand side of this equation? Okay.
du over dy?
Yeah, do you remember? We talked about it last time, right? That's called strain rate. That representing the deformation of the fluid. Okay. U is the velocity, x direction velocity, y is the vertical direction. Okay, that's under the shear stress. Okay, do you understand? Okay, I think some of you don't, maybe didn't understand even in the beginning what is the shear stress strain rate from the previous classes, and then that part you probably need to catch up. Okay, deformation. I'm trying to use layman's terms to talk about it, okay? So that's probably not very strict what I say, but I try to explain with very, very fundamental layman's term, okay? So we apply a kind of force to it, okay? For the Newtonian fluid, the viscosity is a property. It doesn't change, okay? So it has to be equal, right? This is the equation. So if your left-hand side increases, your right-hand side will also increase. So viscosity is constant, don't increase. So the du dy has to increase under a shear stress, okay? Do you understand what I'm talking about here? I want everybody on the same page before I move on. Any questions? Good, okay. So for the non-Newtonian fluid, the left-hand side is still same, increase if you increase the shear stress. The right-hand side, instead of the du dy increase, du dy doesn't change. Then the viscosity increases as a result of increased shear stress, increased force. Okay, that's non-Newtonian fluid. That become very weird. Hey, come on. Hey, viscosity is showing you the stickiness, how hard the fluid is, right? You know, you see a fluid, okay, it's kind of like a regular fluid, very soft, you know, it moves, okay? When you stick your finger to it easily, it's inside the liquid, seems like a liquid, okay? Then suddenly when you apply a force to it, okay, suddenly the property changes. Okay, it becomes harder. You apply a force to it, the property, viscosity increases. The fluid becomes harder. It feels like a solid suddenly. Right? That's kind of weird. Remember, long time ago, there's a show in Discovery Channel talk about that. They build a pool of cornstarch liquid, a pool of liquid with cornstarch or whatever. They mixed it. Oh, so soft. It seems like liquid. You know, it's very, very, very soft. Suddenly, this guy run onto it. on the water, you're not supposed to run it, right? You're gonna sink. And then he jump to it and jump onto the surface. Then it run out. It's not sinking. It's not even dirt. Make his shoe dirty. So why is that? So it seems like it become very hard. It can support the weight of him, this guy. Okay, so why is that? Because you apply a force to it, and the viscosity become much bigger when you apply a force to it. Okay, because you stand on it, jump on it, your weight actually is a force applied on the surface of the water, the surface of that liquid. Okay, then you know it becomes harder. The viscosity increases. Then you don't have the deformation. You don't sink anymore. You can support you then. Okay. I probably can show you that YouTube video. Okay, hold on. Okay, I see a text message here. The surface tension. Who asked this question? Dalen? We're not talking about surface tension. Oh, okay. Oh, you said answer my question. Oh, okay. Why? What is the reason, right? No, it's not surface tension. Okay, surface tension is not that much to support human weight. You know, it's a tiny little bit surface tension. Okay. It's the viscosity. We're talking about viscosity, right? The question I asked must be related to the viscosity. It's because it's a non-Newtonian fluid. Then the viscosity increases when you apply a huge force to it. Okay. Let me share my screen. Let's see. No. Am I sharing a YouTube? Anybody? Give me some response. No?
Yes, it shows the YouTube.
Okay. Is that seeing the Discovery Channel?
Yes.
Okay. Okay, let's play it. Let's see if you can see it.
It's time to break another one. Do I have to make that face?
Hey, look at that. You run on it, right? Come on, my connection is poor too. Well, that's enough. I think enough to show already. The work down that I don't want to spend too much time on. You can just YouTube it. You know, it's there. So that's because of the viscosity increases suddenly. You know, when you apply that force to it, then viscosity increase a lot. I couldn't even stop it. Okay. Okay. Any questions here? So you can actually search. There are a lot of very weird videos about the non-Newtonian fluid on YouTube. Okay, and some of them, like you have a speaker, you put a non-Newtonian fluid on the top of the speaker. When the speaker make noise, okay, it's a sound vibration. Basically, it's a sound force. When you apply that force to that non-Newtonian fluid, then it actually jumps like dance because the viscosity increases. Okay, become a solid like a fluid. Okay, so it actually jump like a block by block. Okay, it's very very interesting, very fun to watch. Okay, so that's non-Newtonian fluid. That's no, how to say this. There's not much theoretical equations to talk about the non-Newtonian fluid because it's too complicated. It's actually material science. Okay, so it's out of scope of this class. But this phenomenon, I would like you to remember, understand. Okay, that's due to the viscosity change due to the external condition. Okay, viscosity suddenly increase. There's another application. I think in the modern bulletproof vessels. Okay, so what you do, you bulletproof. Usually early time, you just use a metal or whatever, of some hard fabric metals, you know, then you can stop the bullet, right? So, but it wouldn't be comfortable, okay, to wear a metal shell on your body. So the design use non-Newtonian fluid, insert the non-Newtonian fluid in between the layers. Okay, so the non-Newtonian fluid, when the bullet hitting it, you know, the bullet hitting it, it's really, really fast and a lot of momentum. So create a lot of force applied to the non-Newtonian fluid inside the bulletproof vessel. Then suddenly the non-Newtonian fluid become harder, much harder. Viscosity increases due to the external force from the bullet. So when the bullet hitting it, it's super hard. When there's nothing to hitting it, it becomes really soft like fluid. Okay, so that's one application. The modern materials, okay, they apply the non-Newtonian fluid to make bulletproof vessel. Okay. Okay, so I guess that's Newtonian fluid and the non-Newtonian fluid, the viscosity. Okay, again, that equation is really, really important to you right now. Okay, you need to know how to use this equation to solve problems. Okay, before I give you an example, let me ask you this. Do you know how to do derivatives? Okay, this class is really relied on your calculus. Okay, if you don't have those calculus knowledge, you will have very hard time in this class. Okay, let me ask you this. Do you know how to do derivative? If I give you a function of velocity, see, velocity, now let's review again. What is velocity in fluid mechanics? Velocity is not a point or not a value, it's a field. Okay, velocity is a field, it's a space. We talk about a volume, a space. So it's a function. Velocity is a function in terms of x, y, z, and the time. Okay, so the velocity, you describe a velocity inside a space, inside a volume. You're trying to describe, you will describe, so velocity you see in this class is always this, it's a space variable. Okay, so in that sense, if I give you a velocity distribution, a velocity function, can you calculate the shear stress to me, for me? I will some homework problem like this. I might give you a quiz for this too, but let me ask you in advance, do you know how to do that?
No.
You don't know how to do derivative? Okay. Let me give you a function. Let's say your u function is this, equal to 5x plus 6y plus 3. Okay, that's what I give you. Okay. First of all, do you know what does that mean? So your x velocity components change with x, change with y in this space, in the target volume. Okay, do you understand this first of all? So that's a concept you have to take. Otherwise, you probably have no hope on this in this class. Okay, do you understand this? Velocity now in this class, talk about fluid mechanics, is a space quantity. Okay, it's a field variable. It tell you in a particular space, which you described in the coordinate system x, y, z, in this particular volume, what are the velocities? Okay, it's not a point value. It's not just a value like a pendulum. You move solid mechanics, the velocity belongs to that pendulum. It's a pendulum velocity. No, you are talking about the velocity in a space. So you have to use a function to describe it. It's not just one velocity. It's thousands or millions of velocity when you talk about it. It's a field variable. First of all, do you understand this? This is very, 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 very critical. Okay, you have to understand this concept. You're trying to describe, in fluid mechanics, you're trying to describe a space, a volume. What does the velocity, what are the velocity inside a target space? Okay, fully understand that. Any questions? I make up this function. Let's say your u velocity. So what you ask, what is u? U is the x component of velocity. Velocity is the vector. So on any given location of that space, you have a vector, right? The velocity is a vector. Okay. If the vector, then it has 3 components: x component of the velocity, y component of velocity, and z component of velocity on that particular location. Okay, we use u, v, and the w to represent the 3 components of the velocity on a particular location. Okay. Okay. Now the knowledge we talked about previously will be useful now, huh? Okay, fully understand. That's why I don't want you to miss any classes. Fully understand this. It's hard if you don't have the concept. It's hard to, understand what the book talk about and what the stuff. Any questions before I continue? No question. Clear enough? 100%. Everybody? Good. Okay. So now you have a function of velocity in this space. Okay, it changes with x, changes with y. Okay, the u velocity. Okay, on any location x and y, you see different u velocities. Okay, so you have this. Then, how do you calculate the shear stress on any given location? On any given location x, y. Tell me, how do you calculate the shear stress? Which equation you will use to calculate the shear stress? Hey guys, please turn on your video if you can. Okay, I can see you, but that seems like I don't have communication with you. I see Arthur's face all the time. You're good. I'm always on. Okay. I also see some other of you. Yeah, but it's half of you don't never show your don't want to show your video. Please turn on your video if you can. If your speed is not internet speed is not that slow, please turn on your video. If I see you, sometimes I can tell you understand or not, right? So answer my question. I'm not asking answer my question myself. What's your question you're going to use to calculate the shear stress on that particular location? If I give you a velocity function like this.
Would you be using the equation on the top of the page?
That's right. You have to use this equation. Exactly. Both of you are right. Okay.
So you'd have to differentiate the u or that's the I hat, right?
That's right. Because viscosity is a constant. It's a value. Okay. We talk about Newtonian fluid, right? So then du dy, you differentiate this u. So in this case, shear stress will be equals to viscosity times du dy. Do you know how to do du dy? It will be 6. Okay. So this is a very simple example. So property, you can find viscosity. So you can calculate the shear stress. Actually, it's a constant shear stress everywhere. You see, the shear stress is not a function of x, y anymore. Okay, so that means it's constant. But it could be, hey, what if this is 2y squared, 6y squared? Then it become what? 12y. Okay, so your shear stress is not a constant either.
Like, so you're saying the y value in your x component of the velocity field is dy whenever it's differentiated?
Yes, exactly.
But you're differentiating u is that whole equation that would go on top and just the y part would go on the bottom? Well, I mean, it'd just be 5 and 6, but won't v equal the y component of the velocity field?
It's separate. Think about this. Vector. You're not familiar with vectors. Okay. When you talk about vector, like a force, when you do in statics and dynamics, how do you deal with the force? You separately calculate fx and fy, right? Fz and also. Same thing here. You deal with a velocity vector. You separately calculate the u, v, and w. But each component u, v, w is a function of x, y, z, and t. Okay, just want to make sure. I should
Okay,
say
so that's just shear stress in that direction.
Shear stress is always in along that direction. Okay, vertical. It's shear stress, right? We talk about the x direction. Yes, you're right. You're right. Definitely, you're right. It's in along x direction shear stress. Okay, so this is but you use the vertical derivative to representing the shear stress. Okay, so that's a good question. That's a good question. Okay, first of all, I think we need to clarify in this class, it's a vector. It's very, very complicated to operate on vectors. So think about just like in the force, when you talk about force in statics and dynamics, force is a vector. So you always look at the vector separately, components separately. Look at the components, right? Fx, Fy, Fz. Here, you look at u, v, and w. But for u, v, and w itself, it is also a function of x, y, z, and t, right? Now, every location, your u, v, w could be all different, okay? So stick with the vector operations. Later, you probably will see the cross product, the dot product, those kind of things. These are all vector operations. If you try to use the general, operation, that would be so complicated, so very long. So you have to use the vector operation sometimes. It look a little bit easier to write. Okay. Is there any question on here how to do the derivative? So if I give you a function for velocity, then you take a derivative du respect to dy. So for example, this case, X is gone, 3 are gone. So 2y squared become 2y. So 6 times 2 is 12y. So then the result, shear stress is also a function of y. So it changes, the shear stress seems like for this particular problem change with y direction. Okay. You're going to deal with those functions like all the times. Okay. Be careful and make sure yourself review the previous knowledge on this. Okay. Okay. Let me give you an actual physical example. Shear stress. Oh, I'm sorry, not shear stress. Yeah, it is shear stress on the viscosity application. The example is in the textbook. Example 2.2. Okay, example 2.2. The problem is this, it have a slope, okay? I think the angle is 20 degrees. Oh, hold on, let me create a new page. This is only one page, it's not enough. At least 10 page, right? I will post these notes, okay? Okay, 10 page, good. So example 2.2, you have a slope like this, 20 degree. Okay, you have a board gonna slide down the slope. Bear with my drawing. Okay, the board is 1 meter by 1 meter. Okay, the weight of the board is 25 Newton. Okay. Okay, before I continue the statement here, okay, tell me what happens this board on this slope physically. Don't read the problem yet. Don't read the problem. I'm just asking you, if you see a problem like this, if you see a ball, if an object stay on the slope like this, what will happen? Will it be sitting on that slope forever, or will it slide down?
Depends on the friction.
Depend on friction, right? Depend on friction. You have friction between the two solid surfaces, okay? If the weight is, the component of the weight is not large enough to overcome the friction, it will stay there. Vice versa. If the component of the weight, this component, okay, you have a weight, you can separate into the two components, right? Again, W is a force, the vector. You have to deal with the vector a lot, right? Okay, so the vector you can separate into two components. If this component in the slope direction, if it's smaller than the frictional force, then it will stay there, right? If it's greater, then it will slide down. Is that right? Is that what we learned in statics? I think this is the statics, right? Friction is in the statics or dynamics. I forgot. Maybe you learned it in statics or dynamics. Okay. The friction is come from what? From that vertical normal force, right? Normal force component. Frictional force is friction coefficient times normal force. Is that right? Hey guys, do you still remember these things? Okay, so the programs like here is building on the previous knowledge. So okay, if you lack of the previous knowledge, then it's hard to proceed, in the future class. Okay. Now, you're an engineer. This is I have a real application for this. For example, you go to Amazon warehouse. Everything is automatic, machine doing it, right? So a package like this, for example, you have a package like this. They put it on a higher location. They slide down a slope to a lower location. Make sure that happens. Maybe a convoy belt or whatever. Okay. Let's say it can slide down on a slope like this. Then it can just automatically move. Okay, but for the manager, you have to control. You can like, every object has different weight. So if it moves down, do you think they have the same acceleration? F equal to ma, right? They might not have the same acceleration. Okay, so it's hard to control the time. If a heavy package, a lighter package, they slide down with a different speed. So with different times. So it's, management point of view, it's difficult to control. So the best optimal way is if I can control the speed of this object sliding down. Okay, if I can make it constant speed. For example, in this problem, they want to make it slide down with the speed 2 centimeters per second. Okay, 2 centimeters per second. Okay, that's a real purpose. So we have, if you slide down with a constant speed, then what? Then the time is constant. Okay, then you can manage it. Okay, the robot down there, okay, every 3 seconds there will be a package coming down. Okay, that serves a purpose, right? Okay. So it said, hey, this thing, you're an engineer. I want you to design for this mechanism to make it slide down at 2 centimeters per second. What can you do? Hey, don't look at the book here. Don't read the problem. Let me just ask you. You're an engineer. You're future engineers, right? You have to have some idea, innovative. Otherwise it's a hard job for you. So what can you do? Okay, based on the information I provide, I'm the boss. You're an engineer. I want you to design a mechanism so that the board can slide down 2 centimeters per second. Okay, so what should be your thought process to attack this problem? I think if I were you, I would think, first of all, if I don't apply anything, if this thing slide down, will it be a constant speed?
You said if it doesn't slide down?
What did you say?
You said if it doesn't slide down?
It does, if it slides down. First of all, if it doesn't slide down, forget about it. I have to make it slide down, right? Okay, so if it slide down, if I don't do anything, will it even make a constant speed?
No.
It won't, right? Everybody agree? It won't, because if it moves down, that means your weight component is bigger than the friction. So you have a force. You have a force going downward. So if you have a force, what happened to the motion? Is the object going to accelerate?
Yes.
Right? So what is your actually the most important part of your design here? Is to me is to make it not sliding down with an acceleration. That's the thing, the task you want to achieve in here. If your design is solution for this. Okay, naturally it will always accelerate. If it moves, then accelerate. Do you agree? Okay. Now the problem say, hey, your boss wanted you to, I don't like this thing be accelerate. Okay, because it's hard for me to manage the time. I want it go with a constant speed. Then I can plan, how many seconds this thing will get down to the bottom. Okay, so that's the key for this design problem. So how to make this thing slide down with constant speed? Then that's what it needs an engineer. Okay, the solution here is you apply lubricants in between this package and the slope. Okay, why you apply lubricant there?
Because you can control the speed with viscosity.
You can control the not only the speed, but you can control the force between them. Okay, you can control the frictional force between them. Okay, that's the only way, because you want to make it a constant speed. Hey, how to make it a constant speed? Constant speed from Newton's what? Which law? First law or second law or third law? First law, right? It has to be no force, or the force has to be balanced. Okay, zero. So the force going down, the force going up has to be exactly the same. Then you can achieve constant speed. Do you agree with that? Okay, that's the thought process I want to convey to you. Okay, you will see difficult problem like this all the time in tests, in quizzes, in your real life. Okay, as an engineer, how you attack the problem. That's the thought process. Hey, okay, I need to make it a constant speed. So how do I make it a constant speed? No other way. Balance the force. Okay, so balance the force. Let's see, how can we balance the force? Okay, so the solution is to put the lubricant there. I think that the oil you put in there, the viscosity for the oil in between is 0.05 Newton second per meter square, right? Okay, assume the oil can be modeled as doesn't matter. Calculate the space between the board and the hump. Okay, so what does it say is you can control the oil. What type of oil you can't? Okay, your boss give you this oil. That's all only lubricant we have in store. Okay, just use that. So what can you control? The lubricant in between. The only thing you can control is how thick you want to put the oil film in between, right? How much oil you want to put it in between, how thick the layer of film should be. Okay, again, don't forget your purpose. Your purpose is to try to balance the force. You have a going down force from the weight, right? You have to create the frictional force exactly the same as the going down force. Then at least you can achieve the constant speed. And how much constant speed, that's another story. It's difficult. This is a difficult problem for the design, all right? Okay, let's see if we can make the constant speed first. Okay, so how do we solve this problem then? Okay, now we'll come back to the paper, pen and paper, right? You have to have a systematic scheme to solve difficult engineering problems. Okay, you are an engineer, they pay you 80,000 a year. It's not just for you to, just pay you that money for nothing, right? You have to do a better job than regular people. Okay, so how to do a better job? Okay, I think the difference between you and the regular people is you know a systematic way. You're supposed to know a systematic engineering ways to solve problems. So in that sense, at the end, if you're good at it, any problem to you is a piece of cake because you have a systematic procedure to solve a problem. Think about the world that will be conquered by AI, right? Eventually, you guys will be replaced by the machine. So what's the advantage of the machine? Because you program a systematic way to solve problems, the machine just follow that forever, never make a mistake. Okay, so you guys need to understand that. I want to convey. I think a lot of class you take, the teacher didn't emphasize on actually the problem solving part of the engineering. Okay, I think in this class it's so difficult. Without the correct, good problem solving skill, you will have trouble with this class. Okay, so you start with a free body diagram. Okay, in many of the problem in this class, I need you to draw the correct free body diagram before you can continue on solving the problem. For example, this problem, without drawing the free body diagram, you have no clue how to solve it. There's no way you solve it directly without even draw something on it, right? Okay. Free body diagram. Any of you have trouble drawing free body diagrams? Okay, Well, what's your major, Dalen?
Mechanical.
You're mechanical? Okay. Your mechanical has no excuse. You're supposed to went through 201, 202, right? All the free body diagrams in there. Okay. So yeah, you probably need to catch up. Okay. If you're chemical, there may be an excuse because you have a lightweight mechanics class like 203, right? Okay. Don't worry. Let's go through it in this class if you don't know how to draw free body diagram. So draw free body diagram, you need to know the body. You need to know the object. Okay. The object you have to you want to study, okay, in that particular problem. So what is the object? Free body diagram. You need to have the body first, right? Tell me what's object you're interested.
Board.
The board, obviously. In this problem is a board, okay? In statics, when you started to talk about those type of static problem, you actually, there are two types, right? One type of problem, simple problem, you only have one object in the situation. Some problem will be more complicated with multiple objects. They're connected to each other. Okay, so this is a more complicated part. They have multiple objects. They connect to each other. Okay, so for that type of problem, you have to draw the free body diagram for each object separately. You're not drawing the whole thing. That makes no sense to draw the board with the lubricant with the slope all together. That's make no sense. So you don't know anything after drawing the free body diagram. So you have to draw the free body diagram separately for each individual object. Okay, right? You have 3 objects in here, right? It's not 2, 3. Okay, the board, the lubricant layer, and the slope. Okay, these are the 3 objects in this case. Okay, so I think, you know, you can start with each one, but I think for this problem, obviously you want to start with the board because that's actually the direct interest. Okay, to solve this problem. So board, draw the board on the paper. Okay. So when you draw this object, you have to separate this object from the other objects, right? There is a rule here. I want everybody to remember. If you're not familiar with free body diagram, that's a rule. If you follow these rules, everything is easy. Okay. Engineer follows the rules, right? Okay. That's because the follows the rule and life will be easier. Okay. So the rule is this. When you detach an object from another object, okay, you draw separately, you have to detach this object from the objects that connect to it. You have to replace the other object by a force, the reaction force. Because between 2 objects, there are always action-reaction forces. So you remove one object, then you have to replace by a force to represent the presence of the other objects. Did I make myself clear here? So let me ask you, what is the board adjacent to, connected to?
A ramp.
No. I said there are 3 objects in this problem. They are the board and the oil film and the ramp. What does the board connect it to?
The oil film.
Oil film, that's what it connected to. Okay, so you detach this board from the oil film. You will need to replace a force to represent the presence of the oil, which means the oil film apply a resistance force to this board. Is that right? You move down, the oil actually pull you. Anything you have friction pulls you, right? So this is the rule you have to remember. Remember, when you draw free body diagram, You draw a single object. If that object connected to any other object, if you just draw this single object diagram, you have to replace a force to represent the presence of the object it connected to. Okay. Is that clear to everybody? And you can name it if you draw a force. That's another rule. You draw a force with an arrow, right? You give a name. Use a letter, whatever letter it's convenient for you. Usually by convention, force will be F, right? Let's say F shear. Shear force from the oil film to this board. Okay. Do this immediately. Every time you draw an object, do this step immediately before you put other forces on it. Before you put other more obvious force on it. Before you forget, okay? Put that. That's the rule for the free body diagram. Otherwise, you won't be able to draw the correct free body diagram. In the quiz, in the exam, every free body diagram, if needed in that problem, I give points to it, okay? You need to draw correctly, okay? Otherwise, there's no hope to solve the problem, okay? Is that clear to everybody so far? Okay, so what are the other forces for this board? The other force seems like more obvious, right?
Weight and normal force.
Actually, normal force, it's a weight, right? Normal force is a reaction to the weight component. If you draw weight, okay, it has a normal force and it has a tangential force, okay? It's a component from the weight. So you will have a support from the to overcome the the component. You're right. Okay. So do you understand these two components from the weight? Let's say weight W normal, W horizontal. How about that? W1, W2. How about that? W1, W2. Do you understand W1, W2? I think that's a fundamental question here also. I want to you 100% understand this. You know how to draw these components, right? Is that right, everybody? Okay. So anything else? Is that it? Did I miss anything? Okay, remember the steps I show you how to solve problem. Okay, don't think about the end answer yet. And the solution, don't care about it. Okay. Just make sure your step is correct. If every step you put on a paper is correct, it will automatically lead you to the correct answer. Okay, that's the difference between an engineer, trained engineer, and regular people. Okay, on solving problem. Check every step, make sure it's correct before you move on. Okay, is this correct? And did I miss anything? Anybody? Give me some feedback.
Do you want to add your angle now, or you just put forces?
Yeah, okay, sure. Thank you. I can put an angle here. This is 20 angle, right? 20 degree, right? Okay, that's a good point. But force-wise, I think that's it. I didn't miss anything. Okay.
Since it's going to be well, the acceleration is 0. I was going to say put the in the direction of motion, put an arrow.
A motion of direction, yeah, sure. So let's say this is the motion. Okay, but I'm pretty sure I will try to ensure motion is constant speed. So that's the motion and no acceleration. I just don't want to say acceleration here because that's what I try to make, try to enable, try to force it to become constant speed. So then force that's 0, you know, it's balanced the force. Okay, good. Now I think I missed one thing. You should mark your XY coordinate. It's a good habit. Okay, XY coordinate actually you can define, right? And for any problem for your convenience. Okay, so for the convenience of this problem, what should be the X and what should be the Y direction?
Direction of motion is X, the direction of the normal force is Y.
So you have to follow the right-hand rule, right? If you want to make the Y direction vertical, the X direction has to be this way. It's the opposite to the motion, but that's fine. It's still along the same direction. Okay, right? X and Y. So otherwise, if you put X positive down there, then the Y has to be going downward. Okay, so I feel the surface normal should be the Y direction. That's more convenient. Okay, so the X has to be the opposite flow direction, opposite movement direction. But at least you have to specify this along the same direction, same angle of the ramp. Okay, very important. If you don't draw, there's some difficult problem, complicated, you will forget, hey, what is my X and Y direction? Okay, because eventually you need to write your force balance, which is the next step. Write your force balance along the coordinate directions. Okay, this is a 2D problem, so you probably have the force balance 2 equations, right? 2 X and Y directions separately. I think the Y, okay, everybody good on this? So we are very strict, okay? Strictly follow the rules. A good engineer, a bad engineer, that's the difference, okay? Strictly follow the rules. Draw this correctly, 100% correct before you move on, okay? Any question, just jump in. If not, I'm continue. I have about 10 minutes. I probably couldn't finish this problem, but I want to cover as much as possible. Okay, so what is the next step? So if the free body diagram part is correct, okay, then what is the next step? You will need to remember this, very important. You will need to write your equation, force balance, based on the free body diagram you draw. Okay, it's not based on the problem statement anymore. Now you translate your problem statement onto the free body diagram. Okay, onto the free body diagram. Then write your equation based on what you draw on the free body diagram. Okay, force balance for the static or dynamic problem, you should have your force balance. If it's 1D, it's just this. If it's a 2D, you have summation Fy equal to 0. That's the equation you start from. Is that right? Okay, let me review this. You have web choices here to make for any statics and the dynamic problem. Okay, today's lecture is really important for you. Probably you want to watch it again. Okay, you have choice for 2D problem. You can maximum write down 3 equations. Is that right? Is that what we learned in statics? Okay, you can write down 3 equations maximum. Okay, you can obviously choose these 2 equations, force balance. You can also choose the moment balance, moment about a point. If it's a rotation problem. If it's problem with the rotation, obviously you want to write the equation about moment. Okay, I hope whatever I say here is not new to you. If it's new to you, then it's a little bit sad. Okay, so it's your choice. So it's from your experience basically to pick 3 equations, and then you can maximum solve for 3 unknowns. Okay, for a 2D problem. Okay, agree? Okay, but sometimes you don't need 3 unknowns. If you only have 1 unknown, then well, what the heck? You just need 1 equation correctly, right? So, but I'm telling you, maximum. Later on, you will see more complicated problem. You have more unknowns. You need more equations. That's maximum a 2D problem can solve. Okay, that's the rule of thumb. Remember this. Okay, now here, obviously, for this problem, there's no rotation. Do you agree? See, I'm showing you how the thought process is when you solve a problem. Okay, is there a rotation or not in this problem? If the answer is no, then no rotation. You obviously go through the force balance equations. Okay, let's help you to make a decision step by step. Every step you have to do it right before you continue, because next step is built on the previous step. For example, here, previous step is a free body diagram. So the equation you write down will build on, based on the free body diagram you write down, you draw down. Okay, then the first choice you want to make is, do I want to do moment equation or want to do the force equation? Obviously, this problem, there's no rotation, so forget about the moment. So you stick with the force balance. Okay, force balance, they have two equations, force balance x direction and the y direction. Okay, can you tell me the x direction force balance? Can you expand this? Okay, if you write down this line on the paper, the test problem, if you write down this summation of force Fx equal to 0, I give it a point or two. That shows me, the reason I give you a point on this is that shows me that you make a good decision, that to choose the force balance equation to continue for this problem, instead of choosing the moment balance equation. Okay, I want you to see every step you write it down correctly. That means that you have the engineering thought process, following the route, goes through the steps. Okay, so write down this. After you look at the free body diagram, okay, I decide to use force balance, summation Fx equal to 0. Good, write it down before you actually put in each letters in there. Okay, to earn some point first. I want you to earn the partial points for any problem. Okay. Okay, so now write down this equation. I'm pretty sure it's right. The next step is expand this equation. Use the letters in the free body diagram. Okay, anybody help me with the next step?
F minus W sine 20.
F, okay. F share, right? That's what you mean, right? This thing, right?
Yeah.
Minus W1. Don't think about the sine cosine yet. Use the ladder on the drawing. Avoid making mistake every step, okay? You get the second step right, then you get some points for the second step too. You get awarded, okay? Equals what?
Zero.
0.
Yeah,
100% right.
So you already have, okay.
Right? Okay, this is the x direction, equal to 0. You get another point or two here after you write it down. Okay, so there's no excuse to score like 8 points out of 100 in my final exam. Okay, but it always happened because they didn't come to my class. Okay, you follow the step, you always get points. Even you have the wrong answer, you get maybe 70. Okay, or 80 even. You just need to write down the steps. Okay, don't give me a blank paper. Okay, now can you go further down? So what is W1? What is W1? Can you
25
calculate
sine
25
20.
times sine 20 equals 0? Bingo. Very good. Okay, see, I don't even know, before I started the process, I don't even know I can actually first calculate the resistance force between the oil and the board. It's so easy. Okay, I can even calculate the internal force between these two objects. Okay, see, I want you to feel this. At the beginning, you don't need to have the answer. You don't need to have what should I find or whatever. Let the process tell you what to find. Okay, so that's very important. Follow the correct process. So what is F shear? The resistance force from the oil to the board. The internal force. Give me a number.
8.55.
8.55 Newton. Great. So let me ask you this. I have only 2 minutes left. I probably couldn't finish it. What does the 8.55 Newton mean to this situation, to this problem? What can this 8.55 Newton bring? Can it bring it to a 2 centimeter per second or something else?
It means it won't change. It won't accelerate.
It won't accelerate. Yes, that value to make sure it will have constant speed, because that leading to a balanced force along the slope, along the ramp. Okay, it will give you a constant speed. But what constant speed? It doesn't tell. Nothing to do with 2 centimeters per second in whatever you go through here, right? Went through here. Okay, so let's continue next time to show, hey, what actually controls the value of the speed is slide down. Now this 8.55, if I put oil there, then it will make it constant speed. Okay, what matters the value of the speed? Okay, it's the thickness of the oil. Okay, control the speed. Okay, we'll continue this next time. Any question? I have 1 minute. So I have maybe 10 seconds. Any question I can entertain? Okay, I just want to give you a feel. This is not a simple problem. Okay, it's not a simple problem. I just want to give you a feel of engineering fluid mechanics problems and what is the way to solve the problem. Okay, if you understand the systematic way to solve the problem, it's no problem is a difficult problem. Okay, that's what I try to convey here. The equation so far is just one equation, so it still can lead to a very difficult problem. Okay, yeah, I guess that's it for today. So see you on Tuesday. Is that good? So far, so good? I didn't receive a lot of response from you yet, so that's why I keep repeating some of the thing. Please communicate with me. Help me, go through this thing. Okay, yeah. Have a good day, and see you on Thursday.
Thank you.
You're welcome.